In the darkness of space, far from our warm little planet, two of the universe's most haunting mysteries may be quietly converging. One is an object so intense, so extreme, it challenges the very fabric of physics, the magnetar. The other is a phenomenon so elusive we're not even sure what it is, dark matter. Alone, either would be the centerpiece of a cosmic thriller. But together, if they are truly connected, they could unlock an understanding of the universe deeper than anything we've imagined. Magnetars are rare and violent. They're remnants of stellar death, ultra-dense neutron stars with magnetic fields a trillion times stronger than anything humans have ever created. In their powerful outbursts and strange behaviors, they hint at forces we don't fully understand. Dark matter is different. It's quiet, hidden. It doesn't shine. It doesn't crash. It doesn't burn. But it has mass, and its gravity holds the universe together. Now, researchers are starting to wonder, what if these two things, the loudest and the quietest, the brightest and the darkest, are connected? What if the most violent stars in the galaxy could help us understand the invisible skeleton of the cosmos? To understand the power of magnetars, imagine this. Take a star at least 8 times the mass of our Sun. Let it live its life, burning through hydrogen and helium until it can no longer support itself. Then let it die in a violent supernova. What's left behind is a collapsed core so dense that a single sugar cube-sized amount of it would weigh more than Mount Everest. This is a neutron star, a kind of cosmic cinder composed almost entirely of neutrons. But some neutron stars go even further. They inherit an intense magnetic field, one so powerful it warps the very space around it. This is a magnetar, with a diameter of about 20 kilometers, smaller than most cities. A magnetar packs in more mass than our entire Sun. Its magnetic field is 100 to 1,000 times stronger than that of ordinary neutron stars, and a quadrillion times stronger than Earth's. If one were placed halfway to the moon, it could erase every credit card on Earth. It would distort the electron clouds and atoms. It could warp the very fabric of vacuum. Magnetars occasionally release giant flares, brief, energetic pulses of X-rays and gamma rays that ripple across the galaxy. In 2004, one such flare from a magnetar 50,000 light-years away briefly disturbed Earth's ionosphere. That's the power we're talking about. They are nature's particle accelerators, nature's reactors, and maybe nature's dark matter detectors. Unlike magnetars, dark matter is invisible. It doesn't explode or flare. It doesn't shine, reflect, or block light. It passes through everything, like a ghost. But it's there. We see its effects everywhere. Galaxies spin faster than they should. Light bends around invisible masses. Clusters of galaxies cling together in ways gravity alone can't explain, unless there's more mass than we can see. Much more. That unseen mass is what we call dark matter. It makes up about 85% of all matter in the universe, yet we don't know what it's made of. It could be a new kind of particle, or something even stranger. Decades of searching with underground detectors, particle colliders, space telescopes have yet to reveal it. We know more about black holes than about dark matter. We've mapped the cosmic microwave background in exquisite detail, but dark matter remains a blank space on the ledger of physics. So, where do we look next? Maybe to the most extreme places in the universe. Here's where the theories get bold and exciting. Some physicists believe that magnetars could actually reveal dark matter. Why? Because under the right conditions, certain types of dark matter might interact with magnetic fields. And no magnetic field is stronger than that of a magnetar. One leading candidate is the axion, a hypothetical particle that could explain dark matter and solve other problems in physics. In intense magnetic fields, axions might convert into photons, particles of light. That means a magnetar, with its enormous magnetic field, might be able to transform invisible particles into visible radiation. Other models suggest that dark matter could accumulate inside neutron stars, altering their mass, changing their spin-down rates, or even triggering their collapse into black holes. If magnetars collapse faster than expected or emit unexpected types of energy, it might be dark matter at work. Imagine that, dead stars acting as natural dark matter laboratories. No particle accelerators needed. No billion-dollar detectors buried underground. Just the universe doing what it does best, running experiments at scale. All we need to do is watch. Scientists are now scanning magnetars with the most sensitive X-ray and gamma-ray telescopes available. They look for strange emissions that might not fit known physics, spikes in energy, subtle shifts in timing, cooling patterns that don't follow standard models. Telescopes like NICER aboard the ISS and the upcoming Athena X-ray Observatory are equipped to detect these kinds of anomalies. They analyze the light, the energy distribution, and even the frequency of pulsations coming from magnetars. Meanwhile, on Earth, physicists are using supercomputers to simulate how dark matter might affect neutron stars. Could it slow their spin? Could it heat them unnaturally? Could it destabilize them from the inside? Some researchers even theorize that magnetars might implode into black holes earlier than expected if enough dark matter accumulates inside them. If we observe more neutron stars collapsing than predicted, especially in dark matter, rich regions of space, that might be the smoking gun. So far, the results are tantalizing, but not conclusive. But the search is only just beginning. If magnetars really are influenced by dark matter, or can help us detect it, the implications would be profound. We could finally learn what dark matter is made of. That alone would reshape modern physics, validating or refuting decades of theories, and possibly opening doors to entirely new realms of understanding. But it would also redefine what neutron stars are. Not just remnants of dead stars, but active participants in the cosmic experiment, amplifiers of invisible physics, touchpoints between what we know and what we have only guessed. We'd also gain better insight into the structure of galaxies, the evolution of the universe, and the behavior of matter under the most extreme conditions imaginable. Magnetars wouldn't just be astrophysical oddities. They would become our windows into the dark. There's a poetic symmetry to this potential connection. Magnetars, born in explosive death, are loud, violent, and brief. They flash and fade like cosmic lightning. Dark matter, ancient and ever-present, is silent, stable, and pervasive. It doesn't roar. It whispers. And yet, these opposites may be connected. In the fury of a magnetar's field, dark matter may leave its mark. In the silence of dark matter's gravity, magnetars may respond. It's a reminder that in the universe, extremes often meet. That the most violent events can teach us about the quietest forces. That death can give rise to discovery. That the universe, in all its vastness, still has secrets to whisper. And perhaps, somewhere in the pulse of a magnetar, we'll finally hear one of those secrets. What is the universe really made of?